Now, this simulation is going to talk about what happens with hydrogen atoms in real life. So you can see this dial is the experiment, what really happens, versus the prediction, what they think hydrogen atoms look like. And so if we shine white light at a hydrogen atom, the white light means that it's white. The white light means that it's light of all colors. And you can see that as most light travels through, some of it gets redirected. And I'm going to speed this up, and we can look at the spectrometer, and it shows you what colors of light in nanometers are emitted. And so you can see that as white light is shown at hydrogen, that it absorbs some of the light and redirects it in different directions, and that the light that is redirected is only these few colors. You have some different types of UV, you have some blue, some green, some red, and a few in the infrared spectrum. Now what we can do is we can look at the different predictions. With the billiard ball model of atoms, nothing really happens, and you can see the spectrometer does not read anything, so that does not explain things. With the plum pudding model, it seems that all of the light that's absorbed gets re-emitted as UV, and so that does not match up with what really happens. With a classical solar system model, I can slow that down so you can see the electron they thought was like a planet that orbits, and it slowly would spiral into the nucleus. The Bohr model, we can speed this up. The Bohr model, you can see the electron is moving to the different rings as it absorbs light, and as it emits it, it is emitting just those same colors. And so you see the Bohr model does explain the hydrogen atom. So when a light of the correct color hits the electron, notice it moves to a different ring, and as the electron falls to an inner ring, it emits light of a certain color, and only these few colors of light are emitted. The de Broglie model, where an electron, instead of being a point, is more thought of as a wave, a string, it does the same thing, and if we speed it up, it also seems to give off the same spectrum that is observed in real life. This only really works for systems with one electron, though. The Schrödinger model, where the electron is represented as a cloud, a smeared out space, and different shapes, is what we're going to cover today. So the reason why people would keep modifying or creating different models of what they thought atoms would look like were because the current models did not explain the behavior of atoms. And de Broglie and Erwin Schrödinger worked off from Bohr's ideas to come up with a model that more accurately predicted what they saw atoms doing in experiments. And so, to come up with a model that better predicted what atoms would do in experiments, de Broglie and Schrödinger developed some mathematical equations that would predict the statistical probability of where an electron would be existing around an atom. And they were not spheres, like Bohr said. And while Bohr said that the electrons would be orbiting as spheres in energy levels, The Schrödinger model, the quantum mechanical model, says that each of those levels is actually split into sublevels. Each shell is split into subshells, and they're also called orbitals. Some of the orbital shapes are spherical, but others are not. And the different shapes of these locations, these orbitals, are called S, P, D, and F. They stand for sharp, principal, diffuse, and fundamental shapes. I'm not going to try to draw the F orbitals, but I will now put in an image that will show all of these. Whereas Bohr said he had an energy level, at this still called principal energy level, there is only one s orbital. At the second Bohr energy level, there is one s orbital and 3 different p orbitals that are all in different orientations. One is in this direction called the x direction along the x-axis. One would be tilted 90 degrees, and that would be called the y-axis, the y direction. And one would be coming out of the paper toward us along the z-axis, and so that's the z orientation. At the next Bohr level, the third Bohr energy level, you start to have d orbitals. So there is one s orbital, the 3 p's, and the 5 different d orbitals, the 5 different d orientation orbitals. And the 5d orbitals all have different orientations, similar to how x, y, and z are the orientations for p, but they're more confusing. And last, at the 4th Bohr energy level, and all of them after that, there are all 4 different types of shapes. There would be one s orbital, 3 different p orbitals, 5 different d orbitals, and 7 different f orbitals. And the orbitals can be holding 2 electrons. So 2 electrons could be in this orbital at one time. Electrons have a property called spin, which is a little bit having to do with their magnetic abilities. And an electron will either have upspin or downspin. And so each single orbital can hold 2 electrons as long as they have opposite spin. In diagrams, electrons are denoted with a small arrow, either halfway pointing up or halfway pointing down. This would represent an upspin electron, and this would represent a downspin electron in diagrams having to do with the Schrödinger model. And if we look here, because each orbital has a max of 2 electrons that it can hold, we can see the first Bohr energy level, there would be 2 electrons max, and this explains why, because there is only an s orbital, and it can hold 2 electrons, one upspin and one downspin. The second Bohr energy level, Bohr said that there were 8 electrons, and now we can see why, that there are 2 electrons that can fit in the s orbital, And because there are 3 different p orbitals, they each can hold 2, and so that would be another 6 for a total of 8 electrons at the second Bohr energy level. The third Bohr energy level, because it has s, 3p, and 5 different d orbitals that each can hold 2 electrons, can hold 18 total. 2 here, 6 because of the 3p orbitals, and another 10 because of the 5d orbitals. And at the fourth Bohr energy level with all of these different orbitals, 1s, 3p, 5d, and 7f, that would be 2 plus another 6 for 8, plus another 10 for 18, plus another 14 for 32 electrons at the fourth Bohr energy level. This diagram is called an Aufbau diagram or an orbital diagram, and it shows boxes to represent each orbital. So this box represents the 1s orbital, where the electrons would be orbiting in a sphere. It can hold 2 electrons, and we would draw them with an up arrow and a down arrow if this orbital were full. This is the 2s, and so it's at the second Bohr level, the second principal energy level, and it can hold 2 electrons. These 3 boxes represent the 3 p orbitals. This might be the x orientation, the y, and the z orientation p orbitals, the side-to-side one, the up and down one, and the out and back. And each can hold 2 electrons. And so you can see the 2s is slightly lower in energy than the 2p. We move on to 3s, the third Bohr energy level, with its 2 electrons that it can hold. The 3p with the 3 different orientations of p. And now the d orbitals with their strange shapes are even higher energy than p or s. And so 3d is represented up here, but notice it's so high energy that it actually overlaps. The 4s is lower in energy than the 3d. And so electrons in ground state will fill the lowest energy boxes, the lowest energy orbitals first. And so if you need, say, 20 electrons, you would start here, you'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. 4s, because it is slightly lower energy, would fill before the 3d orbitals. Then you'd move on to 4p, and then 5s, 4d. So you would follow this going up as you're thinking about where those electrons might exist in an atom. Quantum numbers are a set of 4 numbers that describe a specific electron in an atom, and they can work like coordinates. And those 4 descriptors or numbers are the principal energy level, the sublevel, the orbital orientation, and the electron spin. They're abbreviated with lowercase letters n, lowercase l, lowercase m sub l, and lowercase m sub s, respectively. And n, it describes the principal energy level of that particular electron, which is similar to the Bohr model levels. And so n could be 1, 2, 3, pretty much all the way up to 7 is where they count up to. And those correspond to the shells from the Bohr model. Next is the sublevel, or the orbital shape, and those could be s, p, d, and f, but they want to be described numerically. And so if the value for L, the sublevel, is 0, that's describing an S subshell or sublevel. If it's 1, it's describing P. If it's 2, it's describing a D sublevel. And if it's 3, it's describing F. The orbital orientation is telling you, for instance, of the p orbitals, which one is it talking about? The one where it's going in the x direction, the one in the y direction, or the one in the z direction. And those are described by the letters negative L up to positive L, including 0. And the values for m sub L could be negative L through positive L. And remember, since there's only one s orbital, it's got an L value of 0, and so it can't have an orbital orientation, or it by default is 0. With the electron spin, like I said before, it could be up spin or down spin. Those are denoted with plus 1/2 or negative 1/2, and drawn in diagrams as half of an up arrow or half of a down arrow. And so what you need to do for an electron configuration, it's going to be a description of which subshells or which sublevels have electrons holding them in a specific atom. So for example, lithium with 0 charge, meaning it's neutral, has 3 electrons. And so we can look back to the Aufbau diagram, and the electrons are going to go in the lowest energy levels that can hold them until they're full, and then you would move up to the next one. And so with 3 electrons, you could fit 2 in the 1s energy level, little 1s orbital, and then you would have 1 left and you would put it into the 2s. I'm going to redraw these boxes sideways so that we can hold on to this diagram and reuse it. This box will represent the 1s, the lowest energy, and it gets 2 electrons, one that has an up spin and one that has a down spin. We have 1 electron left to place, so the next sublevel up is a 2s, and it would have just 1 electron. By convention, you typically will just put up spin electrons in if they're singlets. The way that you would write this out is that you would write in the 1s sublevel, and then you put a superscript for 2 to be how many electrons were at that sublevel. So this 1s2 is describing this box, this drawing, and then you would say 2s, because this is the 2s sublevel, and there is only 1 electron. So this first number that comes, the large number, is the principal energy level. The letter afterward is the sublevel, and then the superscript is how many electrons are at that sublevel. PEL is the abbreviation for principal energy level. The letters, these would be S, P, D, or F, would be the sublevel, and the superscript would be how many electrons are at that sublevel. Look at one that's a little bit more complicated. A neutral atom of copper with 29 electrons. So with our first 2 electrons, those would still go into the 1s, the lowest energy orbital. Next, we would go to the 2s, and that would fill up. After 2s, the next higher energy is 2p. I'm going to draw a long box and divide it up into the 3 different p orbitals. And notice as I filled those, I went 1 in each of the boxes before doubling up. Electrons are negative, and so they're going to repel each other. They're going to want to fill orbitals that are at the same energy level with a single electron before doubling up. That's called Hund's rule. I had only accounted for 10 electrons at that point, and so I still needed the next sublevel, 3s. So now we're up to 12 electrons. After 3s, if you look on the diagram, is 3p. We still haven't accounted for all of the electrons, so the next level up from 3p is 4s. We have yet to account for all of the electrons. There are 9 more. We've got 20 accounted for if you count up the arrows. And after 4s is 3d. To write out the electron configuration, once we have this drawing, the electron configuration would be now there's something that is called noble gas notation, and you look at the noble gas, the element that's all the way to the right of the periodic table that comes right before this element, copper, and you would notice that all of this is represented in that noble gases electron configuration, and so you can replace it with the symbol for that noble gas in brackets. Now, since I have this drawing, we'll go over the quantum numbers. Let's say that I wanted to talk about this electron specifically, this electron here. Its 4 quantum numbers. Its principal energy level is 3. Its sublevel, its shape of the orbital is p, and so that means the L value is 1. When you have these, you typically call the one in the middle for the M sub L, the orientation. This would be -1, 0, and +1, so M sub L would be equal to 0. And this is the downspin electron. And so M sub S is -1/2. Next, what I'm going to do is I'm going to write a set of quantum numbers that describe an electron here, and you see if you can figure out which electron it is describing. The principal energy level is 3. L equals 2 means that it's a D sublevel. M sub L being +2 would be, if we're calling this middle one 0, this would be the +2. And the +1/2 is the upspin electron. So those were the basics about both the Bohr model of the atom and the Schrödinger model of the atom. I know that it's a lot to digest, and we'll do a few activities so that you'll be able to see these types of things, these observations that led people to believe these theories about atoms.